This video is brought to you by mywayteaching.com.
In this part, we are going to study about displacement relation in a progressive wave. For a mathematical description of a traveling wave, we need a function of both position x as well as time t. Such a function at every instant should give the shape of the wave at that instant. What is the shape of the wave at any particular instant? That is given by the function which consists of both position x and the time t. Okay. And also at every given location, it should describe the motion of the constituent of the medium at that location. See, for example, if we wish to describe the propagation, or you can say a sinusoidal traveling wave, the corresponding function must also be sinusoidal. Let us take one simple example. We shall take the wave to be transverse, so that if the position of the constituents of the medium is denoted by x, then the displacement from the equilibrium position may be denoted by y. Okay, if you consider a transverse wave, the position is represented by the letter x, and displacement from the equilibrium position that is represented by the letter y. So a sinusoidal traveling wave is then described by, we can write a sinusoidal traveling wave as y x comma t is equal to a sine kx minus omega t plus pi. Here the term pi, this one, in the argument of sine function means equivalently that we are considering a linear combination of sine and cosine functions. Okay, and we can write y x comma t is equal to a sine kx minus wt plus b cos kx minus wt. So from the equation 1, that is this one, and this is the equation 2, from these two equations we can write a is equal to square root of a square plus b square, and this pi, the initial phase angle, is given by tan inverse of b by I, b by a. Okay, see, to understand why this equation 1, it represents a sinusoidal traveling wave, You just take a fixed instant, say t is equal to t naught. You just assume this. Okay. Then the argument of the sine function in equation 1 is simply kx plus constant, isn't it? Thus, the shape of the wave as a function of x is a sine wave. If you take the fixed location, say x is equal to x naught, if you do this, then the argument of the sine function in equation 1 is constant minus omega t. The displacement y at a fixed location thus varies sinusoidally with time. Yes, that is, the constituents of the medium at different positions execute simple harmonic motion. So finally, as t increases, x must increase in the positive direction to keep kx minus wt plus pi constant. Okay, if t increases, x must also rise in a positive way to keep this as constant. Thus, this equation 1, it represents a sinusoidal wave. Traveling along the positive direction of x-axis. Okay. On the other hand, the equation that is y x comma t a sine kx plus wt plus pi, it represents a wave traveling in the negative direction of x-axis. Okay. So in this equation, so we can say this y of xt as displacement as a function of position x and time t, isn't it? And a is the amplitude of wave, this one, and w is angular frequency of the wave, and this k is angular wave number, and this whole, that is kx minus wt plus pi. This is nothing but initial phase angle with the conditions a plus x is equal to 0 and t is equal to 0. Okay, this is the initial phase angle as you can see here. See, this figure shows the plots of equation 1 that we just saw before for different values of time differing by equal intervals of time. So in a wave, the crust is the point of maximum positive displacement. This one, this is the point of the maximum displacement, and this point is trough, this is crust, we know that, and trough it is the point of maximum negative displacement. This is the point of maximum positive displacement, and this is the point of maximum negative displacement. Okay, see, to see how a wave travels, we can fix attention on a crust and see how it propagates with the time. Okay, this is shown by this x cross on the crust. In the same manner, we can see the motion of a particular constituent of the medium at a fixed location, say at the origin of the x-axis. That is shown by the solid dot. So these plots they show that with the time that solid dot at the origin it moves periodically. That is, the particle at the origin oscillate about its mean position as the wave progresses. This is true for any other location also, not only from origin, it's true for any other location. The crust has moved further by a certain distance as the solid dot has completed one full oscillation. So using these plots of this figure, we can define various quantities like amplitude, phase, wavelength, angular wave number. So let us define each of those one by one. Okay. The first one is amplitude and phase. See the equation, that is y of x comma t is equal to a sine kx minus wt plus pi. It varies between 1 and minus 1, isn't it? And the displacement, this y of x comma t, it varies between a and minus a. And we can take a to be a positive constant without any loss of generality, and the a represents the maximum displacement of the constituents of the medium from their equilibrium position, isn't it? That is what it represents. It represents the maximum value in the positive displacement. So the displacement y, it can be positive or negative, but a is always positive. So we call it as amplitude of the wave. Okay, this a is nothing but amplitude of the wave. The amplitude A of a wave such as that it is the magnitude of the maximum is placement of the elements from their equilibrium positions as the wave passes through them. And this quantity which appears in the equation, that is kx minus wt plus pi, appearing as the argument of the sine function, is called phase of the wave. See, the phase of the wave is the argument kx minus wt plus pi of the oscillatory term sine kx minus wt plus pi. So this is the phase. Given the amplitude A, and the phase determines the displacement of the wave at any given position and at any instant. So clearly this pi is the phase at x is equal to 0 and t is equal to 0. So hence pi is called the initial phase angle. By suitable choice of the origin on the x-axis and the initial time, it is possible to have this pi is equal to 0. We can select this pi value to be 0. Thus, there is no loss of generality in dropping that pi in taking the equation. With pi is equal to 0, we can take that equation y of x of t with by making pi is equal to 0.